Hello and welcome to this video on dividing complex numbers. So again, recall that complex numbers are of the form a plus bi, or they can be written in the form a plus bi, where a and b are real, and I is that principal square root of -1. Right? So whenever you see I squared, that's -1. And what we're going to see here is that when we divide two complex numbers, we're trying to write the result, the quotient, we're trying to write the final result in that standard form, that a plus bi, right? Some real number plus some pure imaginary number. And what we're going to see in this video is that in order to do that, it's going to require multiplication by the complex conjugate of the denominator. And I just put out a video on complex conjugates if you want to look for that. We're going to do a search for other videos out there on complex conjugates. And what you're going to see here is very, very similar also to rationalizing a denominator. I put out videos before on rationalizing a denominator with one radical term, rationalizing a denominator with two terms, right? And when we rationalized those denominators with two terms, we multiplied the numerator and denominator by the conjugate, right? So again, this is very similar to that. I've just got a couple examples. So my first example, and both of them were asked to do the same thing, is just simply divide, right? Divide these complex numbers. So I have in the numerator, -4 plus 1i, or -4 plus I, that complex number, divided by, and then 0 plus 3i, but again, no need to write a part of 0, just the number 3i. And as I mentioned, what we're going to do is we're going to see that dividing complex numbers is similar to rationalizing denominators. And in order to do that, something else we need to recall here is when you multiply two complex conjugates, you actually get a real number result. You get a result that does not have I in it, that has a 0 imaginary part. So remember, when you multiply, say, a plus bi by its conjugate, a minus bi, remember, conjugates have the same real part, a, and opposite imaginary parts, b and -b. When you multiply these complex conjugates, what you end up with is the square of the real part, so a squared, plus the square of the imaginary part, b squared. Right? And you could say b squared or -b squared. Either way, it's equal to b squared. And notice how the final result doesn't have I in it. Right? These two numbers have I in it. This I is the square root of -1, but the final result does not. Right? This is a real number only with an imaginary part of 0. Alright, so our goal in division, right, when we're dividing two complex numbers, is to basically rewrite it so that the denominator doesn't have I anymore. That's why I'm saying it's similar to rationalizing denominators. Because remember, I is like a radical, right? I is the square root of -1. So having I in the denominator, is having a non-rational number in the denominator, something, a radical in the denominator. I want to get rid of that. And we'll eventually be able to write our division's result in this standard form, the a plus bi form. Alright, So let's do that here. And what we're going to do is, again, very similar to when we were rationalizing denominators in a previous video. I'm going to multiply the numerator and denominator. Alright, because what you do to the numerator you have to do to the denominator, so that way it's like you're multiplying by 1 and not actually changing the value of the expression. So multiply the numerator and the denominator by the conjugate of the denominator. Alright, and what you're going to see is that's going to get rid of the I in the denominator. So let's do that here. I'm starting off with, the numerator is this negative 4 plus I. It's got multiple terms, so I'm going to put that in parentheses, right, the way I would enter it if I had a calculator. The denominator is, 3 times I, right? Again, you can put that in parentheses too, why not? That's all the numerator, that's all the denominator. Now, what's the conjugate, the complex conjugate of 3i? I'll do that off to the side here. The conjugate of 3i is negative 3i, right? Because again, you can think of 3i as 0 plus 3i, right? That's the same thing as just 3i. And remember, for conjugates, you keep the real part, right? So real part of 0, and then you have the opposite imaginary part. So that has an imaginary part of positive 3. The conjugate would have an imaginary part of negative 3. So you see 0 minus 3i, which is just, negative 3i. Alright, so I'm going to multiply now the numerator and denominator by, the conjugate of 3i, which would be negative 3i. And do the same in the numerator. Alright, now in the numerator, I have, a 2-term expression, negative 4 plus I, multiplied by a 1-term. So I'm just going to be distributing, right, that 1 term over that sum of 2 terms. So in the numerator, I have the following. I have, let's pull this up a little bit. So this is equal to, the numerator, negative 3i times negative 4. Negative times negative, that'd be positive 12i. And then negative 3i times positive I. So negative times positive would be negative. And 3i times I would be 3i squared. Right? Alright, so that's the numerator. Then the denominator, just 1 term times 1 term, right? There's no distributing need to be done down there. So positive 3i times negative 3i would be negative 9i squared. But don't forget, I squared is negative 1. So really what I have here in the numerator is 12i and then minus 3 times negative 1, right? I squared is negative 1. And then the denominator is negative 9 times negative 1. And do you see now, when I multiply two conjugates, I stated up here, the result will be a real number, right? It won't have I anymore. Right? When you multiply 3i and negative 3i, see how there's no more I in the denominator. Alright, so I keep simplifying further. So we have in the numerator 12i, then negative 3 times negative 1, the next term is positive 3, divided by, and then negative 9 times negative 1 in the denominator, that's positive 9. So now the denominator is rationalized, but you're going to see in most texts, we're going to be asked in most texts, and I would like to write in the standard form for a complex number that a plus bi, right, a real number plus a pure imaginary number. So in order to do that, we're going to have to do some splitting up here. Right? The numerator has multiple terms. The denominator, if the numerator has multiple terms, you can divide each term by the denominator, right? It's basically reversing the addition of fractions. So if I have this fraction here, that would result in having 12i divided by 9 plus, and then 3 divided by 9, right? This, if you were adding these two, right, you'd keep the denominator of 9 and then just combine the numerator. So this fraction is indeed equal to this one. And then we simplify some, these two fractions here. You have some common factors. All right, 3 and 9 have a common factor of 3. 3 goes into 3 once. 3 goes into 9, 3 times. You'd have a factor of 3 left over in the denominator. Pardon me. And then 12 and 9 also, in this fraction, the numerator has a factor of 12, the denominator has a factor of 9. They both have factors of 3 as well. When I remove a factor of 3 here, you're left with 4. 3 times 4 is 12. When I remove the divide out the factors of 3, you'd be left with, 3 down there. 3 times 3 is 9. And so what I'm left with, and again, I'm going to write it in this order. So I'm going to switch the order here. I'm going to write the term that doesn't have I, write the real number first, plus, and then the term that does have I second, right, with a coefficient, a real number times I, a real number plus a pure imaginary number. So the real number is this positive 1/3, right? So I have 1/3 as the real part of this result. Then plus, and then this is 4 times I divided by 3, or 4/3 times I, where I write it as a real number times I. This is the same thing as 4 times I all over 3, right? If you multiply the numerators and the denominators. And there you go. This is considered the quotient, the final result of our division. All right. So I started with negative 4 plus I, and I divided it by 3i. The resulting complex number, the complex number that results in this division, is 1/3 plus 4/3 I, right? A real number plus some pure imaginary number. And you should be able to write every number we see as this form here, a plus bi, where a and b are real, and I is the square root of -1. Great. All right, but again, the key to this is what I wrote here. Multiplying the numerator and denominator by the complex conjugate of the denominator, because that will ensure that you have a real number in the denominator and no more I in the denominator, and that'll help you in writing the final result in the standard form. All right, so I have just one more example of this, where we're dividing two complex numbers, and I'll write the final result. I'll write the quotient as another complex number in standard form. So here I have 4 plus 3i in the numerator, divided by, and then another complex number, 1 minus 3i. So as I did last example, and I don't like to mess with the original expression, I'm going to write this again. And because we're going to be multiplying these by something, I'm going to put them in parentheses, right? They both have multiple terms. So right, that whole thing is the numerator, 4 plus 3i, put in parentheses. That whole thing is the denominator, 1 minus 3i, I put in parentheses. And I'm going to multiply the numerator and denominator by the conjugate of the denominator, right? Because I want to have a real number in the denominator, no more I in the denominator. So what's the conjugate of 1 minus 3i? It'd be 1 plus 3i, right? The same real part, but the opposite imaginary part. And I'm doing the same thing to the numerator, right? That way it's like I'm multiplying by 1, right? Anything over itself is 1, so that will not change the value of this expression. Okay. Now in the numerator, I'm going to have to, FOIL, right? Or do a lot of distributing, because the numerator I have a a two-term expression multiplied by another two-term expression. So I'll pick one of these, the 4 plus 3i, and distribute these terms to the other one. Right? So I'll distribute the 4. So in the numerator, I have 4 times 1, that's 4. Then 4 times positive 3i would be plus 12i for the next term in the numerator. Then I'm done with the 4. Move over to the next term in here, the 3i, and distribute that. Alright, 3i times 1 would be positive 3i. And then the positive 3i times positive 3i would be positive 9 times I squared. We'll change that I squared into negative 1 in a minute. Okay. Then the denominator, again, I already mentioned that these are conjugates. Alright, these two expressions in the denominator are conjugates. So if you recognize that, you don't have to do all the foiling. Alright, if you recognize that you're multiplying two complex conjugates, then the final result, right, in the denominator here, will be the real part of these numbers squared, so 1 squared, then plus the imaginary part, negative 3 or 3, either one squared, because when you square 3 or negative 3, you're going to get positive 9 anyway. And notice it will be real. I'll end up with 10 down there. All right. So in the numerator I have 4. The next two terms in the numerator are like terms, right? They both have I attached, I to the first. So 12i plus 3i, that's 15i. And then I'm going to kind of skip right in this. Just remember, I squared, I'll write it up here, I squared is negative 1. So if I have positive 9 times I squared, that's positive 9 times negative 1, that's negative 9. And then, so there's the numerator. The denominator, I'm just going to simplify right now. That's 1 squared is 1 plus, 3 squared, or even negative 3 squared if you wrote that. That's positive 9. 1 plus 9, 10 in the denominator. And totally simplifying the numerator, right? You have these real numbers, 4 and negative 9, that I can put together. 4 minus 9, 4 plus negative 9 would be negative 5. And then you have the imaginary number, the plus 15i. And that is all divided by 10. All right, and this is great. Okay, the number is, the denominator is rationalized, right? 10 is a rational number. You don't have I down there. You don't have the square root of negative 1 down there anymore. But again, I'm going to try to write this so that it's in that a plus bi form, right? The standard form for a complex number. So as I did in the previous example, the numerator has multiple terms. You can divide each of those terms by the denominator, right? So creating the sum of two fractions. So we have, the first fraction, negative 5 divided by 10. Then we have a plus, and then the next fraction, 15 times I divided by 10. And when you simplify these numbers, right, negative 5 tenths, right, 5 goes into 10 twice. This reduces to negative 1/2 for the first, the real part, right, plus, and then 15 over 10. 15 and 10 have a common factor of 5. 5 goes into 15 3 times, 5 goes into 10 twice, so when you divide out the 3, you're left with 3 over 2. So you can write 3i divided by 2, or just 3 halves, 3 over 2 times I. Same thing. And here we go, the final result of our division, written in that standard form, right, that a plus bi form, where a is negative 1/2 and b is, positive 3 halves. All right, so 4 plus 3i, that complex number, divided by 1 minus 3i is equal to negative 1/2 plus 1.5 I, or negative 1/2 plus 3/2 I, another complex number in that standard form for a complex number. Wonderful. Alright, so the key thing to take away from this video is, when you are doing division with complex numbers, or when you see, remember, fractions are division, right? When you see a fraction, where the denominator has an I in it, right? You're dividing complex numbers with imaginary parts to them. The way to get through that is to multiply the numerator and denominator by the complex conjugate of the denominator. And when you multiply complex conjugates, you end up with a number that's real, that doesn't have that imaginary I, and it has a 0 imaginary part left over. And then, of course, do some simple division and simplification afterwards, and you can write anything, any result, as that A plus BI form. All right. And as I like to say at the end of these videos, please do the best you can to try to learn the material on your own before you go out looking for help. I have found over the years that people who take the time and effort to learn something on their own tend to remember that thing for longer and remember it better and are more proud of themselves for it. So read the material, of course, read through the author's examples, perhaps even work out the solutions to an author's examples before you see how the author did them, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously work out some practice, loads of exercises and practice problems. Check the solutions, check for solutions to those if they're made available, so you can see how you're doing and keep track of your progress. And don't give up on a problem or an exercise after 1 or 2 attempts. Very often in mathematics there are several approaches that'll work for any particular problem. So if after several approaches at a problem you're still not seeing how to do it, still not getting it, perhaps you should go back and read the material again. Maybe even a 3rd time, more slowly, more deliberately. Take good notes. Because if you've been working on some problems, there's a good chance you have a better idea as to what the author wants from you, what the author is expecting of you. So then you know better what to look for when you're reading that the material the 2nd or 3rd time. You'll probably catch some things that you didn't catch the first time that'll deepen your understanding and make working on the problems that much easier. All right, but if after that, if after several read-throughs of the material and several attempts at problems you're still not getting it, it's not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online. There's loads of those too. Videos like this one, and I assure you there's plenty of other videos out there better than this one, and they're easy to find. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest thing for most people, is to stay positive about what you're doing. Stay positive about the subject. Believe in your abilities. Maybe even have fun with it. Even through your struggles and failures, and try to get past those frustrations. Because if you can stick with it and get past the frustration and keep at it until you fix your mistakes, those times when you struggle and fail, those are the times you can learn the most, and also learn the most deeply. Because if you're struggling and failing at something and then eventually turn it around, something clicks and you get it, you figure out how to fix your mistakes, you'll remember that material far better than someone who just breezed through it and did it in one fell swoop and never think of it again. Alright, so stay persistent, keep practicing, stay positive, and don't give up. And I just know you're going to get it. And thank you very much for watching.